Perfect. Take it away, Robert.
All right. So like we said, we're going to talk about cryptography, a little bit about myself. So I'm a Microsoft MVP for developer technologies, web, and lately I've been doing a lot of security things, specifically cryptography. I'm a progress champion, Pluralsight author. I gave my Twitter, my email, and blog links there if you want to reach out later. I am going to give you the slides, and what matters today is the conceptual, but I do want you to also see code samples. So I'm a C# developer, so that's what I'm using. I have one version with .NET Framework and one with ASP.NET Core. And so you can use either one of them. There's not much of a difference, and I'll talk through a few things that are different between framework and not. So I'll mention those, but you'll have both of those in the slides, and I'll have a link for that at the end. A little bit of background. So cryptography is the science of keeping messages secure. And there's really four main areas when you think about you want certain things from security. These are things that cryptography can offer. Most people, when you talk about cryptography, immediately go to confidentiality, protecting data from being read. So everybody knows you can do encryption and decryption. People can't see the stuff. So most people, that's what they assume when you talk cryptography. Another important thing is integrity. You want to verify that the data has not been modified. So I'm going to show you how some techniques that take advantage of that. I'm also showing, when I show techniques, I try to show a practical use people have had for it or that you might want to use it for as well. We use it for authentication, so we can identify and validate a user. And we do non-repudiation, which just means if the sender sends you a message, you cannot deny later that you sent a message. So that's going to get into digital signatures. In .NET, the namespace is system.security.cryptography. That's where you're going to find all the things that we're going to talk about today. There are a ton of considerations when you think about cryptography. So the first one is know what your goal is. I see people use techniques that don't make sense for what they want from a goal standpoint. So I'm going to show techniques and map them back to those four different goals. So think about what it is you want. You want confidentiality or you want integrity. That will guide you into what kind of solutions you're going to use from cryptography. Think about how much your data is worth. How long does it need to be secured? So if you have data that needs to be secured for a very long time compared to it's only really important for a day or two, it'll get into key sizes and algorithms and other things, but just be aware of some of those. Think through your primary threats. So it's important. So I worked on an e-commerce site for 25 years. So I think about it from the perspective of I treated the web servers like they were compromisable. So I assumed we could have a 0 day at any time and they could take over my entire machine. So I cared about, obviously, in transit. We're going to talk about HTTPS today. If they could look at your config files, you don't want to have secrets in there. If they're able to take a dump of memory and any transient things that you might have stored in variables could be exposed. Could they modify pages? Can they reverse engineer your assemblies in .NET? So you need to think through all of those threats. Again, I just treat my web server like somebody could take the entire thing over. So I don't want to store secrets there and stuff, which we'll talk about as we go through the talk. Probably have company security policies. So they lay out what you're supposed to use, what algorithms there are supported, and what they expect of you when you use cryptography. Regulatory compliance. So as an e-commerce site, we obviously had PCI. A lot of people are dealing with health data with HIPAA. So there's lots of regulatory compliance you need to be worried about as well. And then layered defenses, and really how many are enough, right? If you want to be totally secure, I've got the secret for you. Take your computer, shut it off, put it in a lead box, and we're done. But that's not terribly useful. So I'm going to talk about don't put all your eggs in one basket. I'm going to show you some layered defenses and why it matters. If you take nothing away from the talk, don't write your own cryptography. So Bruce Schneier is very famous in the cryptography world, has done lots of algorithms. He still creates a new algorithm. He has to vet it with other cryptography folks because they make mistakes. It's not easy stuff. What I want to impress upon you is it's not difficult to use the stuff that in my case is built into .NET. So there are libraries that have been tested. Just don't try to write your own. I've actually run into people that said, I'm just going to do this, nobody will figure that out. That never ends well. So please don't write your own. I want to talk specifically about how .NET algorithms are implemented. So it took me a long time to find this. I just want to show it to you. It only really matters if you still use the .NET framework. You're going to see suffixes on some of the classes. Managed would mean that assembly and that implementation is using C# or .NET code. CNG would be the crypto next generation. It's using that API, or crypto service provider. It's using a really old supported Windows cryptography. In .NET framework, those mattered. And it came into play if you had to be FIPS compliant. You weren't allowed to use managed code because Microsoft never had the managed code certified for FIPS. So again, if you're in the .NET framework world, go out there, read about that stuff. If you're not, it turns out in .NET Core, all of those are actually just wrappers for OS libraries. So they all go to the same place now. And so you'll see I'm not going to use the suffixed ones, but if you see them or you're doing .NET framework, you might be concerned about that. Next thing, if you want to be cross-platform, that's cool. Follow that link and check, because not every feature is available on every platform. So I would hate for you to implement everything on Windows and your cryptography is going great. You go to deploy it to Linux and all of a sudden Bing says that class isn't supported. You don't want to find that out at the end. You want to find out right away. There aren't a lot of them, but it's good to just check and make sure that the classes you're going to use and the techniques are supported if you need to be running it on a different platform. So I'm going to jump into techniques now. So the first one I'm going to talk about is hash functions. So if you've heard of hash functions, they're what's considered a one-way function. So it's really easy to compute in one direction, but some people say impossible to reverse. If you have a good algorithm, it should be very difficult to reverse. And I just gave you an example here where I have a string on the left-hand side and you compute a hash, and it's what they call a data fingerprint. So that represents the whole of what's on the left-hand side. So you're going to want to use this for integrity, and they use it for authentication. So if I were to change, let's say I change this P to a different character, this hash will be, if it's a good algorithm, will be completely different. Okay, so it's just a way for you to get a spot check of, has it been tampered with in any way? And that's why that plays into integrity. Hash algorithms, I'm sure you heard of some of these before. So in .NET, the abstract base is called hash algorithms. I strike out things you shouldn't use. MD5 has been horrible for years, so don't use it. That's why it's struck out. It's not considered secure. SHA family of algorithms, the SHA-1 family, I don't remember how many years ago the PCI said you can't use SHA-1 algorithms anymore and be compliant. There are the SHA-2 family of algorithms. Those are the ones I'm going to show you today. There is actually SHA-3. So they were trying to get ahead of the game. NIST was, they said, we want to be ready if SHA-2 family ever has a flaw that's discovered. We want to know what's next. So they've run a contest. They've chosen the SHA-3 algorithm. I don't list it on here because there's not a .NET implementation of it yet. So my personal policy, I'm not going to go out to George's blog and find his implementation of SHA-3 and trust it with my corporate secrets. So I'm sticking with SHA-2, still completely secure. I just want you to know 3, the contest has happened, the algorithm's chosen, not yet folded into .NET. Another thing I'll mention is there are keyed hash algorithms. So not only do they take your data and compute a hash, they also take a key, and we'll see why that matters. I'm going to focus on the HMAC ones. So let's jump over to some hashing here quick. So I'm going to show you an example. So I've just got hashing. I'm going to show you what it does in the web here. So I've got my text, and that hashes down to, I didn't want Copilot there. It hashes down to this. So I'm going to now walk through what does that code look like. So I'm using Razor Pages. I don't want to focus on any of the web stuff or that kind of techniques. I care about the cryptography, so I'm just going to focus on that. So here's my plain text. You'll see this pattern. So first I'm going to pick my hashing algorithm. I pick the largest bit size because that ends up being the most secure. So I'm using SHA-512. That's part of the SHA-2 family again. I just say create it. I have an object. I showed you here in the code some of those old suffixes. So the managed and the crypto service provider, again, in .NET now, we don't care. .NET Framework, those mean different things. SHA-512 is 512 bits. And so if you do the math, it's got 64 bytes. It's going to be the hash. So a couple things in this kind of loaded statement here. The first is I have a string. That's great. That's what you usually have all over the place. Now the problem is I have a string I want to do some cryptography with, and it only works on bytes. So the first thing I need to do is take that string and convert it into bytes. There's various ways of doing encoding for that. UTF-8 is pretty typical, UTF-16, whatever. I will get the bytes. It's going to take that plain text string and give me back the byte values. It's then going to take that and pass it to the compute hash function, and I get a byte array back out. So again, all the computations are bytes in, bytes out. So that's this. Like I said, you'll see this throughout. It only really matters on these things. If you're doing self-contained code, pick one, it really doesn't matter. If you are working with somebody else, you better make sure you pick the same encoding. It's going to matter if you use UTF-8 and they use UTF-16. So I've got my bytes. So this is the computed value. It's a byte array. I want to show that again on the screen. So I want it to be in a string. There's a whole lot of ways to get bytes into strings. So I'm going to start with the one I like. Each byte is going to have 2 hex characters that represent it. So if I ran this, I can use this bit converter and I say I want to take that to a string, and I'm going to get something like this where each byte is basically the 2 hex characters. I chose to take the dashes out, so you can see I replaced the dashes here. But if we go back to the page, so it did a computation, it computed a hash, and that's what that hash looks like. That will always be that sized. So even if I took back, I'm not going to do this in here. When you have the code, you can do this. If you take a much bigger string as input, it doesn't matter. Hash algorithms, the output size is dependent on the algorithm you choose. So this is because of SHA-512, it's going to be that long. Okay. First thing I want to talk about is integrity. So tamper-proof query strings, I implemented this. We were working on a website. People could come out and on the URL, it had customer number equals, 123. Somebody could go up there and just type customer number equals 124, hit enter, and they're seeing data from someone else, right? That's a problem. And it's not hacking, really. It's you went on the URL that's visible and you changed the value. So that's a problem. In the case of this, I'm just going to say, I don't care if you see what the number is. I don't care about it being visible. So it's not a confidentiality issue. It's an integrity issue. I want to make sure that when the server sends you the stuff, when you come back to the server, that you haven't tampered with it. I'm going to do that using a hash-based message authentication code, which has the key, and we'll talk about why. And so I'm just going to run through some of this code. Well, first I'll show you how it would work. So I've got a link here. I'm going to click it, and up on the URL, you can see I have A equals 1, B equals 2, C equals 3. Again, it's not confidentiality. I don't care if you see those or not. What I don't want is I don't want you to be able to come here, and if this were a customer number, I don't want you to put 3 and hit enter. Okay, couple warnings. Demo. Don't do this in production, right? We don't want to tell hackers how our stuff works and why what they just tried doesn't work. This would be a generic page that faces customers and users. I'm doing this because it's a demo and you want to be able to see what's wrong. So I would never do this, but I need to do this for you to be able to see it. And what it's telling us is the hash values don't match. So let's take a look at how the code works. So if you think about it, I have a URL that I want to have a link to. This is what I want the query string to be. So I'm going to take that query string and I'm going to compute a hash with it. I made a function here that lets me specify that I want it back in hex, and that's whether I want to use a key or not. So let's dive into that. It's going to look very similar to what you saw before. So I come in here, I'm going to choose the 512. Unless I wanted a key, then I'll do this HMAC. The HMAC needs a key. So I'm going to show you how to create random keys that are cryptographically strong later in the talk. Again, don't do this. Don't store your key in the code like this. But again, I want to hand you a demo app just so you can see how this will run, but this isn't where you'd store it. We'll talk about that a bit later. The rest of this looks pretty similar, right? I'm doing the UTF-8, I'm getting bytes, I'm stringing together the data that you gave me, the query string, and then I'm storing some other things here off the end, and I'm computing that hash, okay? I have different ways to get the output, hex or base 64. I just chose to do that in hex. So again, this is the page that sets up the query string. I've got the page it goes to. In a real site, this would be more reusable. So I would have this in a more centralized place. So I don't have to do this on every single page. But what I do is I'm going to pull off the query string that got submitted. So I created a page, I sent it to you. I said B should equal 2. Now you're sending it back to me. You click the link, I'm back on the server. So I'm going to pull off that query string, that A equals 1, B equals 2, C equals 3, whatever those values are. And first thing I'm going to do is say, if that's not on there, somebody tried to delete it, right? The hacker could think, well, if I delete this stuff off the end, like if they came and looked and said, what is all this? They're probably doing hashing. I'm going to take that off. That's not going to work because that's what happens here. And then down here, we just recompute the hash. So you gave me stuff. So I'm going to compute the hash of what it is now. And then I'm going to compare it to what was on the URL. And those things better match. So if I get down here, what's on the URL matches what I computed off this stuff. So now I can say the query string hash values don't match, and therefore it's been tampered with. And as I said, if you come out here, there's all sorts of ways that people could try to hack with the URL and changing values and deleting stuff and trying to guess, maybe I could change that thing to a 2 and it would be okay. So you got to think again about threats and all the ways that somebody abusing your system might try to get to you. Okay. So I just wanted to show you that's a good integrity idea. There's lots of sites that need this because I go to lots of sites where they just have stuff on the URL and you can change it all you want. The other place they use hashing a lot is passwords. So they did Unix years ago. It was great. They had a password file and they were wondering how can we secure your passwords? I'll get into encryption later. If I tried to use encryption, I would need to store a key. So they said, why don't we just, well, when you first create your account, I'll take whatever password you type in, I'll compute a hash of it. And then they stuck that in a file called etc password. It had my user ID and it had my hashed passwords. And they were overly confident, which we'll see in a bit here. But they said, we know that you can't reverse a hash. So they just made the file readable. They didn't care. They said, you can look at it all you want. You can see my users, but you won't be able to reverse the passwords. This is for authentication, right? I'm trying to prove that it's you. Flaw in that logic. So what people did when they came, they said, well, I can't take your hashed value out of the file and reverse it. But I could guess what your password might be. I'll just compute a hash. So it was called a dictionary attack because they literally went through every word in the dictionary and computed a hash of it. So they kept that apple is this, banana is this. Now they don't have to reverse the hash. Now they can just compare all the hashes. When they see a match, they say, well, that match is banana. That's your password. I used to do research in this many, many years ago. And it was about 60-ish% of people's passwords were from the dictionary. So this just gives you some history about why you're not supposed to use those today and why you need better passwords. But I just want to show you what that one would look like. So this is my cracking attempt, right? I create a dictionary. So I would honestly go to an online dictionary and I would take every word out of it and I would compute the hash and then I would store it and I would have the original and the hash. And by the way, thank you, social media. I would go out and look at your Facebook page. I mean, if I were targeting you, I'd find anything you talk about anywhere you are and any one of those words along with combinations of, yes, I know people put exclamations at the end. Whatever I think you might do, I'm going to pre-compute. Then I just have to go say, do any of those hashes match? Okay. So that was hash passwords. And like I said, they ran into problems because of the dictionary attack. So if you've heard of salting before, we're talking about layered defenses now. So they came back and said, well, that kind of sucks, right? We didn't expect that. So let's use salted passwords. So now the idea is each user gets their own random data that they call salt. So Robert's in the password file. Here's his hash password. By the way, here's his random salt. They also chose to put that in there. So now when you come, I'm going to take your password, I'm going to take your random salt, and I'm going to do a hash and put that in the file. Okay, why does that help anything? Well, if you see the second bullet, it really doesn't help you defend a single account. If you went into the file and saw Robert, you'd have my salt, and you would just compute the hash with my salt of the dictionary. Hasn't made that any harder. It has made it, though, a lot harder for you to attack all of the different user IDs in there, because now you can't just pre-compute the hash of the dictionary up front. You have to compute that for every unique value of salt. So they've just made it slightly more difficult to do that across the user group sort of attack, right? And again, I mentioned it really doesn't do anything for an individual password. And again, I'll show you where that's at in here. You can see the hash passwords with salt. Here's some data. Here's the random salt. Again, it wouldn't be embedded here. It would actually be in the password file. And here's some code about how to generate random data we'll talk about later. But pretty much what you've seen before. You're going to compute a hash. This one gets base 64. If I put the salt on, that makes it different. And then if the next level of layering they did, they said, well, okay, that wasn't great. People can go after a single user account. So they added what they called entropy. So they create another piece of random data, but this one they don't store in the password file. So now I've got your password, your unique salt, and this that I stored somewhere securely. Now it's that much harder for a hacker, because now they have to be able to break into my server and get that secret at the end in order to get the right hash to compare. So again, it's layering. If you look today, I'll talk about the kind of the next step here. What do the systems actually use today? They do what's called a work factor. So in .NET, it's called PBKDF2. So the idea with this is it's a function that you can pass what's called a work factor. So instead of running the hash just once, you can say run it 50,000 times or 300,000 times or whatever. I'll show you the code really quick. Again, this is one of the classes that modern systems would be using. .NET, it's called that. So this is the magic. So how does this work? Well, and I'm a Led Zeppelin fan, but that's not actually my password. What I want to do is I want to look at the system I'm running today, and I know every customer needs to log in. I know they're all going to have to do this computation every time they log in, so I don't want to make it take 20 seconds every time it runs. But I have to choose and say, I'm willing to penalize my customers logging in by 2 seconds or whatever number you're happy with. On your current hardware, you keep adjusting this work factor until it takes about 2 seconds. That's what you use then when you run in production. So that way, it's harder again to do the computations. They can do billions of hashes on not that series of equipment. By slowing down every single hash to take 2 seconds or 5 seconds or whatever, that really cripples their ability to pre-compute all of the hashes, if that makes sense. So again, layered, real world, they do all of these things in combination, but this is kind of the most recent, interesting way of doing things, okay? Now we're going to get into confidentiality and stuff. So I just want to mention the terminology that comes up from here. This is all standard stuff you'll hear, so I want you to know what it is. Your original data is going to be called plain text. Encryption is the process that takes your plain text and obscures it. It becomes ciphertext, which is the encrypted data. Decryption is the process to get back to original. The cipher is the algorithm that you use for the encryption and the decryption. And this is what you use for confidentiality. So this is when you talk normal cryptography with people, this is what they're going to focus on and talk about. There's two main classes of it. So the first one, it's called a symmetric algorithm. And so what that means is the encryption and decryption use the same secret key. So I'll show you the diagram quick. I have plain text. I know the secret key, so I can encrypt it. It becomes ciphertext. I give it to somebody else. They also have the secret key, so they can decrypt it, and they're back to the original plain text. In transit or storage, whatever, people can't see what it means unless you have the secret key. People attack this primarily by doing a brute force key search. So in other words, modern algorithms, they're not going to probably break. The algorithms have been tested a lot. I can't say, obviously, that there's never a flaw in .NET's implementation of AES or something, so that's possible. People that try to break into it generally have to do a brute force search. So they have to try every secret key. So this is cool, it's fast. The problem is the key distribution is very difficult, right? If I picked one of you out of the chat list and said, I got a secret for you, and I said, I'm going to send it to you here, and then I think about it, how am I going to send you a secret key? It's kind of the chicken and egg, right? I have no way to securely give you the secret key in that situation. So that's kind of the Achilles heel of this. There's a lot of protocols we'll talk about that use symmetric within them, and they're great to know and they're fast, but that's one of the issues with it.
Hey, Robert.
Yeah.
We had a couple items in the chat.
Okay.
One person asked, what about pepper?
I've heard of
but apparently that is a thing.
Apparently that is a thing. I have not actually looked up what it is. I can't remember what they call that. I almost think that's the extra entropy that I was adding at the end, but don't quote me on it. I'll have to go look.
Yeah.
This is the first, I've done this a lot. This is the first time I've had one of those kind of questions I didn't have an answer for, so I will find out.
Nice. Someone wins a prize, but they're virtual, so we can't give it to them.
That's right.
If I am
secret.
And then what?
If I may say something,
sure.
From what I've been told in another class, pepper is where you don't store where the salt is basically just not stored anywhere.
Well, they have to store it. I mean, when it comes back to me, you're going to give me your password. I have to know the secret stuff that was used to hash your password, or I can't even let you in again, right? It's not a hacker problem at that point. It's just, so
like,
when you,
I mean, you still know the password and the hash. It's just that I don't know how to explain it. From what I understand, once it's been hashed and everything, they don't store the hash, the stuff they added anywhere else.
Okay, I will have to look at that.
I don't really know how to explain it myself.
Okay.
But
I have heard the term. I've just it's never come up in any of the algorithms and stuff that I'm using. So I will find that out. But I know that I have to be able to reconstruct what you need to log in. So somewhere that's got to be kept. Otherwise, I wouldn't be able to reproduce the hash. Like if I use something the first time I hash your password and you come back and give me your password again, if I don't know what that was, it's game over and I can't authenticate you. So let me look up the pepper stuff and I'll put it in the meetup. I'll put it in the comments when I have a good description of what that is, if that works.
Oh, and there's a link now in the chat.
All right.
I did have a question, and that was, how does quantum computing change the game?
So I'm going to let me hold off on that till I get to asymmetric algorithms, because that's the primary place that people are concerned. I mean, they're concerned in general that quantum will just be that much faster, but asymmetric is specifically what they're very worried about will get broken. So if you hold right after symmetric, I'll get into that one. So there's lots of algorithms. DES is not safe. Triple DES, I should probably strike out. AES is the US government approved. So you're going to see it used in a lot of places. That's what I see used everywhere. So I'm going to focus on that class. In .NET, symmetric algorithms are called block ciphers. So what that means is it takes your data. You're going to have a block size. It's going to take off that number of characters, or eventually bytes, and do encryption on that, and then it's going to kind of set that aside. So it's got a little piece of the ciphertext. Then they go to the next block. So they just keep doing that. So the chances that your message fits exactly in a block size, like the very last one's not likely to end just at the block size. So they need to do some padding. There's different ways to pad that ending block. In general, every time you talk cryptography, if you do more random is always going to be better. So you could pad it with zeros. I'm going to skip ahead and just say this is the padding that's recommended because it's putting random data in the extra stuff off the end of that. Okay. I'm going to show you why you have to do these things or it'll be a problem. There's also different modes. So the first mode is called ECB. And what it does is it says, I'm going to take the first block, I'm going to create the ciphertext, I'm going to set it aside. It takes the next block, does the same thing. It turns out that in ECB mode, you're only looking at individual blocks. So it turns out if the first block of the message is exactly the same as any other block, the ciphertext for that will be the same. Again, I'll show you why that's a problem. We're going to use CBC. What that one does is it says, I'm going to take the first block, encrypt it. I'm going to use the output of that encryption as some randomness that gets added into the cryptography for the second block. Okay. So it's going to keep doing that down the line. So then you say, well, that's cool, but how do you get random data for the first block? That's what's called an initialization vector. An initialization vector is random data used to seed the encryption of that first block. I use cryptography a lot. I've read this a lot. I'm not a cryptographer. They say it doesn't need to be secret, which is always, I guess, kind of a head scratcher for me. It's like, I would think you'd want that to be secret, but it turns out you don't need it to be. And I didn't mention it. Good algorithms, people want algorithms they can see. If somebody has an algorithm where you got to keep the algorithm secret, that's a problem. You want the algorithm to be well known so it's implemented right. The only thing that needs to be secret is the key. Okay. So the thing with an initialization vector, never reuse it. So even though you can, so when I use it, I pass it in, I get all this encryption, I send the ciphertext to who I'm sending it to. I have to give them the initialization vector. So that's in the clear. You get the ciphertext. However, if I ever reuse the initialization vector, that's where it's going to hurt me because now I've lost some of the randomness. If I were sending you just yes or no, I take an initialization vector with yes, you're going to see ciphertext. If I reuse that and put in yes again, that ciphertext is going to be the same. So the important thing with initialization vectors are just have it always be random. And .NET's going to kind of do the, what I've heard called the pit of success, right? It's going to put you in a situation when you're calling it that they're going to set you up as much as they can to not be flawed in your use of things like initialization vectors. So I'm just going to do test. I just want to show you what the web page looks like. So here's the ciphertext. You'll notice it's not hex. I'm using base 64. The way you can tell is base 64 encoded stuff usually has 1 or 2 equals at the end. So I did the encryption. I got bytes. I did base 64 encoding for the ciphertext and the initialization vector. I give those to someone else. They know the secret key, so they can get back where we started. Okay. So I want to show you what that code is going to look like. All right, so we go into symmetric and we'll go into the base. All right, so I've got a couple properties here that store the plain text and stuff you saw. It's my way of showing it on the screen. I'm going to use AES again and do the create. By default, it's going to use the biggest key size. It's going to use CBC, which is what you want. This is a bit in question. You can do better with this padding mode, so I did that here. But I do that create, I do the padding mode, and then I have the secret key. Again, you're not going to store it like this, but to give it to you, there's the secret key. The other thing I want to impress on you is that is not a lot of code, right? So I've created a cipher, it comes back out, and then I say, hey, I want to do encryption. So there's my cipher. I get the initialization vector. I talked about when I create this class in .NET, it's going to give me a random initialization vector every time. So that was the pit of success stuff, right? That I would have to work to reuse an initialization vector using this class in .NET. So I need to give that to the other person. So I'm going to store it. I'm going to base 64. Like I said, there's various reasons you use one or the other. It usually doesn't matter. And then doing the encryption, I just say I want to create the encryptor. Again, I have a string. I need to get it into a byte array. So I do the UTF-8 get bytes. And then this is the call that actually does the encryption, gives me back the ciphertext. And then again, I just chose to base 64 it and show it on the screen. So the other thing I want you to see is that is not a lot of code to get very serious cryptography. This is, again, don't write your own stuff, right? I mean, this is tested and it's not hard to use like this if you know the right way to use things. So I'm going to show you that ECB thing. There's a good example of this. It's called the ECB penguin. So here's the penguin, right? If I used ECB mode for symmetric, every single thing in here that is the same will have the same ciphertext, right? Because you're only looking at, here's the data, here's the ciphertext. You're not doing any of the initialization vector stuff. So the problem is, if you look in the middle, each one of the original values has a different value now, but the problem is all the ones that are the same. So you can make out that's a penguin, right? If you're using CBC in proper modes, it's completely random. You're going to see this, which is what you want. So just be aware ECB is very problematic. People ask, why do they have it there then? Some people have to support older systems that maybe only had that, which would be unfortunate if you need to do that. Don't do that if you have a choice, because that's the kind of stuff it's going to leak because it's not doing each block, if that makes sense. Okay.
Hey, Robert,
Yeah.
question for you.
Yep.
So you're showing a lot of .NET, the built-in stuff to the framework.
Yep.
Is that performant enough, or do you recommend alternatives?
As far as if I use cryptography in .NET, am I worried that it's going to be slow?
Well, compared to alternatives. I mean, cryptography, I mean, right? I mean, you're going to have overhead. But
yep.
yeah, is Microsoft's implementation that's built into the framework highly performant, or is it, are there better libraries to use performance-wise?
Okay. Well, I'll answer the way that the approach that I took with it. I wanted to stay within .NET sphere. I wanted to know that I could trust the algorithm. So I ran my own perf tests. Like, I want to do hashing and I want to measure how long it takes to do a hash. Modern hardware, a single run, you'll probably never notice the difference. If you're worried about it, you can do that, right? You can set up a test and you can even say run it 10,000 times and I want to see the difference between this and another framework. I never ran into anything with the encryption I was using that would make me stray away from wanting to stay in Microsoft, C#, kind of that sphere, if that makes sense. Had I run into stuff, then I would have had the questions that you're asking. Should I find a third party? Do I trust the third party? And by the way, this is not meant to be C# centric. It's only because I do that. I hope that these libraries exist in nearly every framework and language, right?
Well, so it would if it was .NET, right? It's all MSIL.
Yeah, I guess what I'm getting at is if you were using any other language, AES has probably got an implementation in that framework or language, or at least a third party that somebody wrote AES so that when you're doing Java, for instance, you'd have it. That, you know what I mean? So the conceptual matters. So back to your specific question, I never ran into perf problems with the stuff that I use from .NET for encryption that would drive me to go even look at a third party.
Okay, thanks.
Yeah. Yep, no problem.
It's built into the framework.
Yes. Yeah. Yep.
So technically, it would be NuGet now. It used to be able to get all of it. Like you got the whole .NET framework. Now you get the parts of the framework you need by downloading NuGets.
And I would say, I mean, if this is new and you're just using it, I would do some testing, right? Put it in what you're going to use it for and make sure that it works. Don't, every implementation is different. I did that. I would do that if I were you. I haven't run into problems with it for me. So, okay, so that's symmetric. The other choice is what's called asymmetric algorithm. So the idea was they said, boy, secret key is a problem. We can't do key distribution. It'd be great if we had a way to solve that. So what they came up with is what they call the public-private key pairs. And so this is, they use like RSA. There's various people around the same time. I've read a lot of the history stuff. So the idea was they took primary numbers and there's a lot of math. They basically are saying if you had just the public or the private, it's mathematically impossible with today's stuff to derive the public from the private or vice versa. So it's very likely you would have my public key and you'd want to find out my private key. Today, it's computationally not going to happen for many, many years for you to figure out public from my private. So this is right where you had the question of quantum computers. They're afraid quantum computers are going to make this specific type of math easy, in which case all of our asymmetric algorithms are going to have a problem. They haven't proven that yet. They don't have quantum computers that we all have on our desktop. So people have been watching it for years. That is the threat. There's always been this good guy, bad guy, ratcheting, right? They're putting their money on someone will find a quantum computer way to do better encryption, not using what we're using now that won't have the flaws, and they hope the good guys are beating the bad guys, if that makes sense. But this is squarely where there's a risk. If you hear about quantums and they say cryptography will be broken, it's because they believe they'll be able to figure out your private from your public fast enough that we're all in danger. And this is all that HTTPS is built on, so it's a pretty serious discussion. That's the risk. That makes sense? So a couple notes. It's generally 1,000 times slower to run than symmetric, so that's unfortunate. Hey, it's cool. We have this public-private key thing. Unfortunately, you use it for actual encryption, and it's that much slower. It's also, there are limits in size for what you can actually encrypt. And so I'm just going to show you the picture here, so hopefully this makes sense. If I want to send you a message, I'm going to get your public key. I do plain text encryption with your public key, knowing that the only person who can reverse it is you with a private key, the receiver. So the receiver will use their private key and decrypt and get back here. Super cool. Yay. People say there's no key distribution problem. I have to trust this, right? I mean, this is kind of the Achilles heel with this. If somebody acted like you and said, here's my public key for Ralph or whoever, and they really weren't Ralph, and that's really not their public key, I'm encrypting stuff that this attacker has a private key for. So everybody always says this solves it. In my mind, doesn't solve it. You have to be concerned about where do you pull the receiver's public key, and that's a decision for you, right? If I wanted to, I could go to LinkedIn and put it in my profile. Do I want to put it in Twitter profile, wherever, right? It's going to boil down to, can people trust that's really my public key? Okay. So if you do have the right public key, that's how asymmetric works. Like I said, it's slower, and we'll talk about some of that. I'm going to focus on RSA for this. That's implemented in .NET. So let's go look at how that works. I'll actually run it once just so you get to see it again. And I see I skipped something I want to show you. Here's my decrypt. I'm going to take a segue back to something I didn't mention. So I talked about creating random data. So like when I showed you this symmetric, how do you create the keys for that? When you get the code, there's a page here that will let you spit out random data. So the way you need to do it, you have to use what's called a cryptographically strong random number generator, or it's not really random. So if you used to use VB or some frameworks to say, give me a random number between 1 and 100, it's not very random, right? They have what's literally called a cryptographically strong random number generator. On computers, these algorithms are pretty good at being random, but they're not perfect. So there've been some kind of innovative things that I think are kind of cool. So Cloudflare, part of their needing random data, they decided that they would create a wall of lava lamps. So if you've ever heard this, they have literally a wall of lava lamps somewhere in California. When they need random data, they take a picture of the current state of those lava lamps and use that as some of the randomness to generate their random stuff, because computers aren't truly random. They're reaching out of computers into the real world to pull some of that, which I think is kind of cool. And then I saw they also have one in London that's not quite as well known, but the pendulums. So the same thing, they have a wall of so again, just know that these are just some of the ways that people are actually pulling out random data from outside the computer systems. So, okay. So let me get back over to where we were here in the code. So here in the asymmetric stuff, I've got this page. So again, when I want to create a cipher, I use rsa.create. I store, so in this case, I'm just showing an example of this is actually someone's public key. In the real world where I store that, I could certainly store it in my database of customers because I have my database, I have you, here's your public key. It's not something that needs to be hidden, it's public. I'd pull it from there when I need to encrypt something for you. So here I do the create cipher and then the rest of the encryption. So this is what you've seen before, right? It takes a string and does UTF-8 on it to get back a byte array. And then here we're doing the encryption. I'll warn you that this padding is a more random padding than PKCS1. So just be aware that you'd rather use that for your padding when you use AES. And then I compute the ciphertext and I base 64 encode it again. So again, this is public-private key stuff with .NET. There's not much code in here at all, right? Another reason why we want to focus on reusable libraries and stuff rather than write it ourselves. So that was asymmetric. Where do we use this? So I told you that my website is compromisable. And so what I do is if I wanted to do encryption, right? If I want to take your credit card number and I want to encrypt it, that's not something that I don't want to use symmetric and have a secret key that I have to store somewhere. What I can do instead is I can generate an RSA key pair, public-private. I'll put the public key on my web server because if anybody compromises my web server, they're not getting a secret. So as soon as I take your credit card, I use public key, I encrypt it. There's nothing on the web server that someone could pull to do the decryption. The actual private key would be somewhere inside on another system that's behind firewalls and stuff. Basically, the part that goes right before they talk to the credit card processor. You need to be able to do that decrypt to send to them. Okay. It's meant for small amounts of data. So I'm just going to show you again, that's just one of the flaws or concerns about asymmetric. So I'm going to do the demo quick. So we did this, right? So we do the encrypt, we do the decrypt, all's good. So we saw that. Now, where will we use that? So I'm going to use it. I'm going to pretend that I'm taking data. So for instance, you're giving me your credit card number on my public website. I do the encrypt. I used a public key to do that. So if I go back into the code here, the website encrypt, I have my public key that I want to use for encryption. And I just do the same stuff I did before. But the key is, because I'm not doing symmetric, it's not a secret. The public key, you can see that doesn't matter. As soon as I do the encryption now, I can pass that around, store it in a database, whatever I need to do. Someone needs the private key to be able to break it. Okay, so that's a practical use of, I need to encrypt things, but I don't want it to be exposed on a public website. That's an approach. Some of the credit card processors have gone farther and said, when you work with them, they will give you a public key. So they'll say, here's your public key. This is where you encrypt it. As soon as you encrypt with that, your company does not have the private key anywhere. So no one at your company could possibly, you're not going to get broken into, expose your key and have people that saw your encrypted credit cards get broken. I don't have the key. That's the credit card processor. So they just give me a public. So that's just a practical thing that people do today to get that kind of confidentiality without worrying about losing it. And again, credit cards are small numbers, so it fits below the limit of how much you can encrypt with asymmetric. Okay. Okay, so now we'll talk about digital signatures. They do both integrity and non-repudiation. In other words, they're set up to say the contract or whatever the data is, you're going to take that, you're going to have it set up so that you can check the integrity and prove that I'm the one who sent it. So it's easiest to look at this through a diagram. I made it a little extra hard. So by default, digital signatures do not care about confidentiality. So typically I would think contracts and things, you might want confidentiality. So I rolled all of it in one big demo. So that's this. I take my plain text, I'm sending it to you. So I take your public key, I encrypt it. We already saw that. That's standard asymmetric stuff. The secret is I'm going to take the ciphertext, I'm going to compute a hash with it. So now I have a hash value. That's where I'm going to get my integrity. If you try to mess with that ciphertext and tamper with it, I'm going to know because the hash won't match anymore. I take that hash, I'm going to take my private key and do encryption on the hash. That becomes a signature. And this is always the head scratcher part. Why am I using my private key? It's because you have my public. So by the time I'm done, I have yours. So it's encrypted, only you can decrypt it. You can tell it hasn't been tampered with. And you can prove that it came from my private key because the signature with my public key will say that I was the one who did the signing of that hash. I'll send the ciphertext and the signature. So let's look at what that looks like. I won't spend quite as much time on digging into this. I just want to impress on you. That's a lot of stuff happening. And again, it won't require a whole lot of code. So I'm going to look at the sender only for now. I need your public key again. This is the demo. That'd probably be in a database or somewhere. I need to have my private key. Again, I'd have that securely stored, not here, but I need that. And then here's the work. So I'm going to create a sender cipher. That's with my stuff. I'm going to create a receiver cipher with RSA. That's your public key. That's my super secret credit card number if you want to write it down quick. I do the stuff I did before. I need to take it out of bytes and put it into a byte array. Down here, I just do the encryption like I always did. So this is just standard AES encryption of that credit card. I compute a hash. That's exactly what I did before. This is where the difference comes in. .NET has a special class. I can say, give it me the sender cipher, which has my private key, choose the algorithm you want to use for signing, and then create a signature, and it returns a byte array. And then here, I just take both the ciphertext and the signature in base 64 and code it. And then I drop it onto my URL. So if I go to this page, signatures. Here's my URL. I've got my secret. That's my ciphertext. And then if I go further off to the right, there's going to be the signature. The sender then can use my public key and its private key, reverse that whole thing, and there's my credit card number again. So again, not a lot of code to pull all of that off. I've got confidentiality, so you can't see it. I have hashing, so if anybody messes with it in transit, we'll know. And we have proof that I'm the one who signed it. The only real recourse people have against that is if somebody said you signed it and I want to say I didn't, I'd have to say that my private key must have been hacked or stolen, and therefore all of my other signatures are called into question. So most people feel that people won't go that route because everything else they have would suddenly be called into question. That's really the only safety you have, right? That's what somebody would say. They lost their private key. That makes sense? Okay, so let's talk about real practical how this stuff gets used. If you know about HTTPS, you should be using it everywhere. If you know Troy Hunt, have I been pwned? Somebody said, well, I only have a static website. Why do I care? And he said, do you give me permission? And they should think about the answer to this. Do you give me permission to show you why you should be using HTTPS? And then he just really messed with the traffic coming to the client, which was hilarious. Use HTTPS. So how does HTTPS work? I have a website. I want to provide it to other people. So I'm going to go out and create a private public key pair. I take my public key and I'm going to give it to what's called a certificate authority. So Let's Encrypt is a free one, worked great. Don't let people tell you got to pay for them. The cryptography isn't any better or worse with Let's Encrypt versus others. So same algorithms and such. So I will pass my public key. I will prove to Let's Encrypt that I own the web server I'm hosting it on. Sometimes they have me add a record to DNS. Sometimes I have to put a file in the root of the website. It basically proves that I'm the person that does control that site. And here's my public key. Certificate authority will digitally sign my public key and give it back to me. So now I host that on my web server. Okay. A browser comes along, it comes to my site. I say, hey, I want to use HTTPS. The browsers know well-known CAs. They know about Let's Encrypt. All the reputable certificate authorities the browsers know about. So they're going to pull down my certificate. They're going to check that this was signed by Let's Encrypt using Let's Encrypt's public key, because they know that it's well-known. So the browser then says, yes, I believe that this certificate's okay. They'll pull my public key out. Okay. Why do they do that? Well, the browser wants to talk to me. We don't want to use asymmetric algorithms because they're slow. So the browser is going to choose a random symmetric key. It's going to take my server's public key, encrypt it. So it's going to use asymmetric so that it can hand me a symmetric key. The server will use its private key. It'll pull out and say, hey, great, we have a symmetric key. We both know what it is. It was transmitted securely because we did it using asymmetric. And now all of the stuff happens using symmetric, which is fast. And it's protected by that symmetric key. So it just kind of shows you most of the parts of everything we discussed and how they roll up into what they would call more of a protocol, right? It's using these certificate pieces to put together something useful. I'm going to talk about key sizes. So key sizes, the trade-off is really performance and security. So when you asked the question of me before, I also ran tests of if I use higher bits for AES or RSA, is it going to be too slow? Symmetric, I can get up to 256. Asymmetric, I can get up to 4096. Again, you do all of your own considerations, do your perf testing. I'm not going to get fired by having a few milliseconds slower, but I will get fired if somebody does a brute force on a key because I chose a poor key size. So in symmetric, I could have picked 128. It's not twice as strong to be 256 bits. Every bit adds basically a double. So if you think of the difference between symmetric 128-bit versus 256, is just a massive improvement from a security standpoint using the 256. So my policy, I'm just going to use the highest ones I can. Again, if you're concerned, do a quick perf test. I'd be shocked if you're going to see the difference between those, especially with one run. Key storage is where it gets a little hand wavy. I talked about, so key storage is one of the biggest problems, right? If I have a secret key and I'm using it on an e-commerce site that I treat as compromisable, that's a problem. How did I get around that? I don't store secrets on my web server, right? That's why I was using a public-private key. But if you do have to store keys somewhere. Basically, I would say look to the platform that you're on, like Azure Key Vault, other systems, wherever you're going to be running this. They've tried to create areas that are more secure than you're going to create to store some of those secrets. I really won't talk much more about this. It's a 101. Again, I've always avoided it by using the public key trick I've had for my websites, and that's where my environment is. You need to think about it, right? If you allow it to be in strings, like what I showed you, because I'm handing you this code, right? If I've got my secret right here, that's a horrible idea because you can reverse .NET assemblies. So when this gets compiled, if I could steal your assembly, I can reverse engineer and find this value embedded in your stuff. So that's why you don't want to just put it in code. Okay. Quick summary, don't write your own. I mean, if you haven't picked up on anything else, the likelihood that you're going to exceed is extremely low. If you are a brilliant cryptographer, great. Prove it. do stuff and have it vetted by other cryptographers. Don't just try to use something that you think is secret on your own system, and that's not going to turn out well. Use trusted algorithms and implementations. Like I said, AES is a really well-known algorithm. I trust .NET's implementations. It's been used a lot. It's been tested a lot, but look into, that's kind of where things would fall down, right? If George did write his own implementation of AES, it's not likely to be as secure as what Microsoft writes. Think about your goals. So if you're doing integrity, you want to use hashing, not encryption. Those are the two that get messed up the most. People say, I'm hashing or I'm encrypting when they're really doing one or the other, or they're using the wrong thing because they don't tie it back to what their goal is. So if you want integrity or authentication, you want to use hashing. Generally, for encryption, use symmetric unless you have special needs to not, because it's fast. The special needs for asymmetric are digital signatures, key exchange, etc. And you can build most of the protocols you'll see today that people are using for serious things are a combination of asymmetric to do key exchanges and then symmetric to do all the real work. Again, know your threats, choose your proper countermeasures. I am a Pluralsight author. I've got the intro to cryptography goes into all this stuff. Most of it is still pretty current. Similar what you see, it's longer and it gets into some of the history. I like cryptography just in general, the past, the history, things that have happened with it. I got this practical, you're talking about Python before, practical cryptography in Python. I don't happen to know Python, but I love this book because they talk about how do you use AES securely. The things I talked about, like how do you do padding right? Why don't you use ECB? It's very well described in that book. So if you're looking for some justification about what I've been talking about as far as using libraries correctly, that's an excellent book. I talked about Bruce Schneier. I don't have it with me. A Big Thick Applied Cryptography is kind of the seminal work, they would say, for cryptography. It's older. I've looked through it. I'm not the kind of person that's going to look at AES and see how is all the bit shifting and how's that all work and all the math, because I really don't care. He, though, does cover, again, how do you use AES properly to be secure? And that's what I took from that. And then both of these other two are just good backgrounds again. And if you are the type that want to see all the nerdy functions in math, party on, that would be a good book. I also really enjoy these other two. The code book just talks about all the history, like what was Caesar cipher? How did they break it with frequency analysis? What did they do with Vignere then cipher to get around some of the frequency analysis? So it's really cool. They do make a kids version of the same book. So my daughter used to do crypto talks or, secret code talks for kids at that conference. They had a family track. So we'd do secret codes, and it was cool because that book was the kind of the companion of the adult version. And then the kids version talks about the same things, but easier for them to follow. So again, if you like all the history, how did the Allies break Enigma? All of those things. Why did they? Because the Germans always said the same thing at the beginning of their messages, which cut some of their randomness. So it made it substantially less random. So anyways, there's a lot of cool stuff in there for history. Twitter, email, blog. That's my link to the slides and the code. So again, you'll have C#, .NET Framework, and .NET, and also the slides. So with that, let me know if anybody has any questions to go through.
Did we have any questions? I got you. Oh, well, weren't you going to talk about the quantum computer stuff, or did I miss that in the bathroom?
Yes, yeah. So the quantum stuff, what they're concerned about, let me go back to, they're worried that quantum is going to make the ability to take, so these are prime factors. So there's a math between the public and private key. Today, being able to take my public key and try to figure out the secret key, which is your goal, right? I mean, if you want to get to my stuff, you got to get my private key. That is cryptographic. I mean, it's just computationally extremely difficult. And you can go back in the books and they say, the time of the universe times whatever is not going to happen with current computing. Quantum computers, they're afraid that they'll be able to do the math between this and the prime number factoring is going to be simple. Again, I'm not mathematical or a cryptographer to explain the math part of why that matters. They just say you'll be able to get a private key from a public key a lot easier in the quantum, which is what they're worried about. So they're afraid if that's true, all of our asymmetric key exchanges, the HTTPS, all that stuff is going to be considered obsolete. And so I mentioned that's the risk, right? People are saying, well, we hope by the time those are available and people could use them, by that point we have, quantum alternatives and stuff. Not a great answer, just because you have all of this old code that's not going to just get switched day one. And the other thing that's concerning, when I talked at the beginning about how long does your data need to be secured, China and some of our adversaries are just sucking up encrypted data right now. They can't break it today, but they're sucking it all in and storing it for the day that if quantum then suddenly says, here's your key, now I can get you private. Whammo, here's all this interesting stuff.
Right.
That's the concern. And so, pretty much squarely targets this, much worse than anything else. So, does that make sense?
Yeah. Thank you. Does anyone have any other questions? No? Hold on. We got one. Hold on.
Okay, go ahead.
Oh yeah, you come up here. Yeah.
So this is just a curiosity regarding the earlier question about performance. I was wondering whether the math that goes into a lot of the cyclical algorithms, does this lend itself well to running on a GPU? And if so, I wonder if you know whether Microsoft's implementation can choose to run it on a GPU.
I don't know the second part. I will say that the hash cracking rigs typically have used GPUs. And again, I don't know all the implementation stuff of why they're using that and why that's more effective on a GPU, but the hashing stuff, I know when they talk about hardware that's seriously trying to do a lot of hashes quickly, that's what they're using. But I don't know if Microsoft, like if I can specify in any of the code to say, I want this to be one place versus the other. I haven't looked for it. I won't say it's not there. Yeah.
Plus, you might want to take a look at. I'm just shot in the dark on that one. In a server environment, having to send the payload over to the GPU to do the work and get the result back might actually be less performant than having the general purpose processor do it, because ever since, oh gosh, what was it? The Pentium 3, I think, they have specialized circuitry for encryption and decryption on the main CPU. So that being considered, you actually wouldn't want to go off chip because you're just doing one, right? Now, if you're trying to create a whole bunch of hashes, then it makes sense, I think, to go and do a payload or try and let the GPU do it. But if you're just doing one, then the return probably would be too slow.
Yeah, and for me, I don't get much. Again, the stuff that I'm doing, like you said, I'm not trying to run so many computations that it surfaces as a problem. The stuff that I'm doing, I don't really care. It's milliseconds,
Yeah.
But I just know that for whatever reason, the hashing tends to go that way, just because of I don't know if it's how the implementations are or whatever, but
yeah.
But I haven't seen a way to do what you said. Like if I knew I was going to do a lot of serious stuff, I don't know if I can shunt it to force it to go somewhere or somewhere else. So in .NET.
Yeah. I thought because I remember years ago, was it Shane? I don't know. He was doing an example of quantum computing. It was called, what was it called? Like Q was like the .NET quantum computing implementation, and when you spun it up, it ran on the GPU.
Okay.
So whatever you built, it was built to run on a GPU. But it wasn't CUDA. I mean, you could use CUDA, right? I mean, it was agnostic, but it was built to run on GPUs, and then get the result back to the CPU. I don't remember what it was. I know it wasn't. I'm fairly certain it was an Indy.net Consortium video. I think it was at IndyAlt.net. So I don't know if they which has been shut down for a few years now. But it was yeah. I don't know. And if you follow me afterwards, I'll see if Shane still has any of his info about it. Because he might. All right. Any other questions? Okay. Well, Robert, always a pleasure, friend.
Yeah, thank
Thank you. Let's give a yay.
The virtual
And-
yay.
Yay, virtual yay. Awesome. Well, thanks, and hopefully we have you again soon. And
Yeah.
be safe out there. We're getting tornadoes and stuff. I don't recall where you're located.
Southwest Minnesota, and we're getting
Oh yeah, you're
snow.
gonna get hit.
Yeah, we're
Yeah.
good. Like I was telling my wife, I think these are the largest snowflakes I've ever seen. They're just
Yeah.
they're honking. So
I heard that there was like some massive downpour hitting a good swath of the Midwest. And like they had and like, but it's not hitting Minnesota. That one didn't hit Minnesota, but it's barely missing Indiana. But it's gonna just probably ruin Kentucky. I mean, it looked really bad. But then again, I'm not a meteorologist, so I have no idea what it meant.
right.
They said it was effectively like a river in the sky, and
Wow.
that's what was going to be dumped on all these people, and people would be getting in trouble.
That doesn't
Mhm.
sound good.
No. All right.
right.
Well, thank
Thanks
you
for having me.
On
Good to
that
see you.
note, right? All right. Thanks, Robert.
right.
Be well,
Yep.
be safe, friend. Talk with
All
you
right.
soon.
See ya.
Ciao.